Hi, in this video we'll be discussing Euclid of Alexandria and his massively influential work, The Elements. Here's an artist rendering of him there, and here's another one on this page. Notice uh, it says, instead of just Euclid, it's Euclides, which is how the Greeks would refer to him. Euclid was uh, probably born and certainly lived in Alexandria, Egypt. We only have approximations for his birth and death dates, so about 325 BCE to about 265 BCE, or if you want to think, flourished around 300 BCE. He was the most prominent and influential mathematician teacher of the ancient world. He was a leader and teacher at the what became the most important school of mathematics, the Library and Museum at Alexandria. Library, of course, is what you would think of a library, it's a place where they kept records and books. In this case, of course, it would be papyrus scrolls for the papyrus and scrolls for the most part. Museum means a temple to the muses, which is basically a school or a place where scholars could come and think and research. The At the museum there and library, um, the scholars were supported by the state, so there was a definite move by the leaders of Egypt at this time. So at this time, this would have been uh, Ptolemy the First, who was one of the heirs of uh, Alexander when Alexander died, Alexander the Great. His kingdom was broken up into, well, especially three big pieces, and Ptolemy uh, ruled one of those in Egypt, and um, he definitely supported uh, academia, right? The supported thinking. And so this museum, think of that basically, first of all, well, like an institution of higher learning where the research was done, but then also it became a school. Um, Euclid is most famous for his work, The Elements, which we're going to talk about a little bit more here. It is 13 books, the first textbook of mathematics. It collected all earlier knowledge. Probably little of it was actually Euclid's original mathematics, but the organization and presentation was definitely Euclid's. It gave an axiomatic treatment of geometry, which is what it's most famous for, but it included other things besides strictly geometry. It definitely included uh, some number results, number theory type results, but these were thought of geometrically. It's the second most translated work in history, only after the Bible. Uh, is the only one that's more translated, and it really forms the foundation of Western mathematical thought. In fact, a lot of Western culture and period. Okay. So this next map is kind of an interesting one that came from Encyclopedia Britannica Online, and this shows the location of many of the mathematicians that we've talked about, that you read about in your textbook, and some of them we will be talking about a little bit later on in the course. Um, but for example, this is a large scale map here. We can see Africa, Europe, Middle East, Mediterranean Sea right there in the middle. Okay, and that's zoomed into this big map, and then this little portion right here, we're zooming in a little closer still. So, for example, Thales and Anaximander were at Miletus, right in here. Pythagoras started out over here at Samos and eventually ended up over here. So here's Samos and then ended up over here at Croton. We'll talk a little bit later and next week about Archimedes, and he was at Syracuse there. There's where Zeno was, Zeno of Elea, and some different ones here that we're going to be talking about. Proclus is an important one later on up here at Constantinople, which became a really major city. Aristophanes down here. But I want you to look down here at Alexandria at the mouth of the Nile River in Egypt, there on the Mediterranean Sea, and look how many really important mathematicians there are there. Ptolemy, not the ruler Ptolemy, a different one. Pappus, Menelaus, Diophantus, Heron, Hypatia, and of course Euclid there. So this, you can see that this became a major center just by the number of important names that are there listed in this here. So this map's a pretty good little map to kind of give you an idea where several things are. If we look at the zoomed in part here, um, for example, Athens is right in here. Plato, Theaetetus was there. Uh, so you have a lot of interesting mathematicians and where they were. Eudoxus was down here. So Eudoxus and Theaetetus were two of the most prominent ones prior to Euclid. Now, some of these mathematicians that you see listed here have certainly, well, all of them have contributed significantly to mathematical growth, particularly, and all of these are considered Greek mathematicians, even though these are not in modern day Greece where they're living now, or the countries now where they are not modern day Greece. But all of these are Greek mathematicians. It's the Greek culture. Either these are all considered either part of Greece or at least had that Greek culture throughout this area. And these have captured the imagination of folks, particularly say artists throughout time. Most of these people are, well, actually probably all of them are so old and that we don't even have contemporaneous um, artist renderings of most of them, or even maybe any of them. Um, but sometimes you'll have later works that will bring them out. This one is a painting called The School of Athens by Raphael, and he puts his interpretation of many of the famous mathematicians in this picture. And Euclid is right down here teaching some geometry to some students there. Okay, and so there's artist renderings of mathematicians. Of course, this was done much, much later. So let's talk about Euclid's works a little bit. So, as is the case with these ancient scholars, we often have some of their works and often don't have some of their works. One, of course, is the most famous one is the Elements. Turns out to be one of the most influential books in the history of the world. So that would have contained, or does contain, the basis of foundational work in mathematics that Euclid collected at that time. So the elements means the basics, the foundations. So that's kind of where you start. It's followed up with data, which has 94 propositions. Um, it kind of covers what properties of figures can be deduced if other properties are given. So these later works assume that you've kind of worked through the elements first, and you can use those things to help you prove the things in these 94 propositions in data. So data is more advanced work, or at least more advanced mathematics that builds on the earlier stuff. On divisions, it's talking about constructions used to divide a figure into two parts with areas of a given ratio. Optics was the first Greek work on perspective, and phenomena was introduction to mathematical astronomy. Now we have references to some of Euclid's other works, but so far at least, we have not found any of these works, may never find them. There's one on surface loci, porisms, conics, book of fallacies, and even one on the elements of music. And so these were all related to things that Euclid wrote. So here's a quote from Proclus, a later major Greek mathematician. Not much younger than these pupils of Plato is Euclid, who put together the elements, arranging in order many of Eudoxus's theorems, perfecting many of Thales', and also bringing to irrefutable demonstration the things which had only been loosely proved by his predecessors. This man lived at the time of the first Ptolemy, for Archimedes, who followed closely upon the first Ptolemy, makes mention of Euclid. And further, they say that Ptolemy once asked him if there was a shortened way to geometry than the elements, to which he replied that there is no royal road to geometry. He is therefore younger than Plato's circle, but older than Aristophanes and Archimedes. For these were contemporaries, as Aristophanes somewhere says. In his aim, he was a Platonist, being in sympathy with his philosophy, whence he made the end of his whole elements the construction of the so-called Platonic figures. So I like this story. You know, uh, the 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 Pharaoh king of Egypt there, Ptolemy, says, uh, you know, I want a shortcut basically, and the story goes that Euclid said there's no royal road to geometry. There's no shortcuts. If you're going to learn it, you have to go through the steps, work through work through the elements, work through things step by step to build that knowledge. Okay. Um, so these Platonic figures, what they're referring to there, are the five different, uh, sometimes called Platonic solids, Platonic figures, also known as the regular uh, polyhedra. And there are five of them. Okay, one is the tetrahedron. So what is a regular polyhedron? Well, a polyhedron in general is a closed surface. It's made up out of faces, which are, if it's a regular uh, polyhedron, the faces are regular polygons, you know, equilateral triangles, squares, regular pentagons, and they are put together like this so that all the faces are congruent to each other. So it turns out there's um, just five of them possible. A tetrahedron has four sides. Tetra means four. Um, there's an octahedron that's made with eight sides, and a icosahedron with 20 sides. So this one has three of the triangles coming together at vertex. This one has, well, you can't, the other one's behind here. There's a fourth one there, and then there's five of them coming together here. Those are all made with equilateral triangles. There's one made with squares, a regular hexahedron or cube, and then there's a one made with pentagons, regular pentagons. That's the dodecahedron, 12 sides are faces. Okay, so this has four faces. This has 4 points. I would call them four vertices. You might call them corners informally, but they're called vertices. And then the edges are the sides of the um, regular sides of the faces, right? The sides of these regular polygons. So this is an edge. There's a vertex, vertex. This whole side here is a face, which is of course that triangle plus its interior. So we have those here. So tetrahedron, regular one has four faces, four vertices, six edges. Regular octahedron has eight faces, six vertices, 12 edges. The cube has six faces, eight vertices, 12 edges, and so forth. You can see those here. Now, these also became associated with several other different things. For here, you can see in this particular one how they were associated with what they felt were elements that made up things: fire, air, earth, water, and ether. They also thought, oh, this is really interesting. Some different mathematicians later on looked at this and said, hey, there are five of these. There are five planets. Well, the ones you can see with the naked eye. And so there must be some relationship there to the planets as well. So there are all kinds of interesting things that people did with these solids. Plato felt they were very important, hence they've got become associated with his name. So here's a kind of abbreviated contents of what's in the 13 books, or if you want to call them chapters, of the elements. Book 1 is definitions, postulates, axioms, the basics of plane geometry, includes the Pythagorean theorem, theorems about angles, areas, triangles, constructions. The foundation of geometry is right there. Book 2 is congruence of rectangles and squares, geometric algebra, including things like the golden ratio. I'm certainly not saying everything that's in these books, just giving you a rough idea. Book 3 has circles and some of their properties. Book 4 has the incircle and circumcircle of a triangle and talks a little bit about regular polygons. And so those 4 books for sure were what we would think of as the basis of elementary Euclidean plane geometry. But book 5 continues on to talk about proportions. 6 is similar figures. Book 7 has some elementary number theory. Book 8 has geometric sequences of natural numbers. Book 9 has prime numbers that are shows that prime numbers are an inference set. Talks about perfect numbers. Book 10 is talk about incommensurables, or in other words, irrational numbers. Book 11 to the end starts talking about some 3D solid geometry. Book 12 has volume formulas or volumes of cones, pyramids, and cylinders. And as we just said, it ends with book 13. The ending of it works its way up to the Platonic solids. So notice, I started to say formula a while ago. They didn't really think in terms of algebraic formulas like we did, but rather they thought geometrically. So let's talk briefly about the basic setup of the first book in the Elements. Again, it's where we introduce axiomatic Euclidean plane geometry. The book starts with 23 definitions, things like a point is that which has a position but no dimension. A line is a length without breadth. A surface is that which has both length and breadth. It defines different kinds of angles and triangles and circle, etc. Now, some of these things would not be definitions in our current looking at geometry. We would, in fact, we would take things like points and lines to be undefined terms, which are given meaning by the postulates. And what's interesting is that these definitions are not really used very much in the later parts of the text. So there's some idea that some of these may have been added by a later author and attached to the first of the book when someone copied this later. Of course, we don't have the original copy that Euclid would have made. Next follows what are called the 5 common notions. Actually, I think probably the next is the postulates and then the common notions. But we have common notions, which sometimes we'll call them axioms. Things that are equal, things which equal the same thing are also equal one another. If equals are added to equals, then the wholes are equal. If equals are subtracted from equals, then the remainders are equal. Things which coincide with one another equal one another, and the whole is greater than the part. And then there are 5 postulates. The first postulate, to draw a straight line from any point to any point. To produce a finite straight line continuously in a straight line. To describe a circle with any center and radius, and all right angles equal one another. And if a straight line falling on 2 straight lines makes the interior angle on the same side less than 2 right angles, the 2 straight line, if produced indefinitely, meet on that side on which the angle is less than the 2 right angles. Okay. So these things were thought of as necessary, first of all, to be able to go forward. It was brilliant that Euclid, or perhaps those before Euclid, realized that we have to make some basic assumptions upon which we build everything else. So that's the basic idea of this axiomatic system, that we accept these axioms or postulates and we build everything from that. And so that is revolutionary. If you notice, even the postulates were thought of as constructibility with a compass and straight edge. Many of the proofs were how to construct the geometric figures with justifications based on early results in the postulates. This axiomatic system was built up from these five postulates and five common notions, and they were built up sequentially, with earlier propositions being used as justification steps in the proofs of later propositions. But don't you take a look at these postulates? One thing is that these were thought of as things that just were somewhat obvious about the way the world actually is. So whenever Euclid and the later geometers and even mathematicians for centuries were looking at these, they thought of the postulates as sort of obvious um, representations of the real world, or at least not maybe the real world, maybe an idealized version of the real world. And so there was never any real um, idea that there might be some other postulates you might want to use. And it wasn't until much, much later, whenever they came up with the ideas of hyperbolic geometry, that people began to question that approach and think that, hey, maybe we could start with some different axioms. We'll talk more about that a little bit later. But look back at these postulates. Um, basically the first one's saying we can take a line segment. We can take any 2 points and connect them up with a line segment. Any 2 points determine a line segment at least. And to produce a finite straight line continuously in a straight line. In other words, you can take any line segment and extend it to another line segment of any arbitrarily length. To describe a circle with any center and radius, we can, given any center and any radius, we can construct a circle. And we can, of course, we can do it with a compass and a straight edge, or compass there. The straight edge would be the tool that you could use for the first two. And all right angles are equal to one another. That's what they're really saying there is space is kind of homogeneous. That when you move things around, that that basically things land on top of each other. So as idea of a superposition, that you could take uh, a figure and move it on top of another one that was equal or congruent. Today we'd use the term congruent. But look at this fifth one. One of these things is not quite like the others, right? So this last one here seems to be more complicated. It seems to be different than the others. And in fact, Euclid even went out of his way to try to prove things without it when possible. But this last one, the fifth one, this one right here, is known as the Euclid's fifth postulate. It's also known as the parallel postulate. It turns out that it's equivalent to saying that given any line and a point not on the line, there's exactly one line through the point parallel to the given line. So it looked to mathematicians that it could be proved from the other postulates. And for centuries, many mathematicians tried to prove Euclid's fifth postulate. And this ultimately led to a lot of mathematical discovery. The closest, of course, that they got was to see that it was equivalent to some other statement, like the one above. And of course, eventually, many centuries later, it was discovered that this postulate is actually independent of the others, leading to the discovery of hyperbolic geometry and ultimately other non-Euclidean geometries. And we'll talk about this revolutionary discovery more in later weeks. So let me just give you an idea of how the elements get started here. Here's the first proposition. to construct an equilateral triangle on a finite straight line. In other words, if you can you can you can make you can construct a equilateral triangle, or an equilateral triangle exists given with its side being any line segment. Okay, so the proof would wait something like this. Let AB be the given finite straight line. Of course, by that we mean actually a line segment. It is required to construct an equilateral triangle on the straight line AB. Describe the circle BCD with center A and radius AB. Again, describe the circle ACE with center B and radius BA. Join the straight lines CA and CB from point C, at which the circles cut one another to the points A and B. Now, since point A is the center of the circle CDB, therefore AC equals AB. Again, since point B is the center of the circle CAE, therefore BC equals BA. But AC was proved equal to AB, therefore each of the straight lines AC and BC equals AB. And things which equal the same things also equal one another, therefore AC also equals BC. Therefore, the three straight lines AC, AB, and BC equal one another. Therefore, the triangle ABC is equilateral and has been constructed on the given finite straight line AB. So notice that this is definitely constructive in form, right? And it's basically telling you how to actually go about constructing an equilateral triangle using a compass and a straight edge. So here, my challenge to you is actually pull out a compass and straight edge and work through this proof one step at a time, doing the actual constructions, and you'll see what's going on. Uh, if you use, you can do the same sort of thing virtually with some program like GeoGebra using only the compass and straight edge tools, and you'll go through the same steps. It's basically how you would construct an equilateral triangle given a line segment, even in GeoGebra as well. So proofs were constructive in nature. Constructions were done with a compass and a straight edge. So numbers were thought of as lengths and areas. They did make a distinction between what they call numbers, or natural numbers, or even rational numbers, versus measurements, which included the irrational numbers. For example, in the Pythagorean theorem, when they say the square of the sides, they are literally thinking of areas of squares, not necessarily just thinking of them as numbers, right? And so when Euclid proves the Pythagorean theorem, this is the basic diagram that he works with, and he makes these constructions here and uses those constructions to work out a proof. So numbers were thought of as lengths, areas, and so forth. Even natural numbers, which were certainly there for counting, they're often thought of geometrically. For example, triangular numbers, square numbers, and so forth. For example, we know the perfect squares. 1 square is 1, 2 squares is 4, 3 squares is 9, 4 squares is 16. They can think of these as actually arranged in a square. That's why they're called squares, right? And so here's 1 square is just 1, 2 square forms this square here, 3 square forms this one, 4 square forms this one. And you can see these built up recursively in this picture, because here we have a certain square, let's say 3 square here, and to get to the next one, so that's n square is 3 square, which is that 9. And look what we do. We add 3 here, and one more in the corner. We've added this L-shaped thing. It's called a gnomon. Okay, so this gnomon, this L-shaped thing, was added to that. And so this gives us what we would maybe today express algebraically. N squared plus 2n plus 1 is n plus 1 squared. We might actually prove this by doing some algebra on this. The Greeks would have thought of this way right here as a geometric construction. And this would have been their idea of the proof or illustration of that. Just like you have square numbers or triangular numbers. So here's 1, and then you add 2 to that, and then you add 3, and you add 4, and you add 5. So this would be a sequence 1, 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, and so forth. And they are easily arranged in a triangle here. As you can see here, each start with the upper left here, and then each one is adding as we go down like that. There's also some interesting patterns that you might see. Here's one, for example, with a sums of consecutive triangular numbers. So there's 1, the first triangular number. 3 is the second triangular number, so you have 2 here, but you make a triangle. 3 is the next one, 3 here, 3 at the bottom, and make a triangle. Here's the fourth one here, which is 10. The fifth one is 15. And so we can get that, but it's kind of interesting when you take 2 of them and add them together. Look what you get. 1 plus 3 is 4 square, and take 3 plus 6 is 9, or 3 square, and so forth. You can see that as adding 2 of these successive ones to get the perfect squares. So that can show you something about that. So some interesting things there. You might actually think about how you might write out a proof that goes along with that. So later mathematicians realized that Euclid was actually assuming some other properties, postulates, other than those that he actually stated as postulates. And some different mathematicians along the way worked on making that a little better. In the early 20th century, David Hilbert developed a version of Euclidean geometry that fixed these defects, and versions based on Hilbert's work are pretty much the standard of studying geometry now. But Euclid's work was the basis for Hilbert's work. And Euclid's systematic approach at proving propositions based upon a few assumed postulates and collecting this knowledge in one work, carefully developing an axiomatic system, was absolutely revolutionary. The Elements was so well done that pretty much everything before that was mostly lost. Remember that it's back then there was no printing press or way of mass producing things. To have a copy of a work, you had to very carefully write things out by hand, and painstakingly do that and try to preserve that knowledge. And so, even just writing materials were not that easy to come by. And the people who could do the copying and so forth, very time consuming. So it was very hard to copy things. Well, once the Elements came around, it was copied over and over and over again, and became widespread in its usage, and probably other of Euclid's works, but especially the Elements. And it became very much the foundation for a quality education for many centuries. It's still today the underlying foundation of development of all Western mathematics. So it's a very influential work. It was so well done that there was really no point in recopying earlier things, because it really collected all the Greek mathematics, at least the basics there, that had been developed up to that point. Again, we don't know whether Euclid, how much of it was his actual ideas and things that he proved, or how much he was just taking earlier works. Certainly he was taking earlier works and copying those and organizing, but the organization was almost undoubtedly his, and it was brilliant how this was laid out, and it formed the foundation of a lot of later thought, not only mathematical thought, but other thoughts as well. It heavily influenced Greek philosophy and so forth as well. I'm going to follow this video with a couple of videos from my college geometry course that I originally made for that, that talk a little bit more about the role of an axiomatic system and and give you a little bit more ideas behind that. Some of that's going to be more of our modern approach, but it also is going to go back to talking about Euclid's approach a little bit. If you've had my college geometry class, you probably already studied this material and seen that, but you might want to review that, or uh, if not, you can watch those videos as well. But once again, the elements ultimately transformed intellectual thought forever.